Good morning, Year 10s. How's it going, guys? Oh, Zana's in first. What's up? Nicely done, Callista. It's hilarious. Jack, first comment, and then he missed it. No! And someone already liked. Lol. Right, guys, last lesson of Ionic today, folks. Last lesson. So let's crack on. Share screen. I'm very aware that my YouTube video is going to be running on my laptop, and I just want to turn that off to save myself the bandwidth. There we go. Right, screen's up. Let's crack on. Okay, guys, so just checking that's all okay. Yeah, that's all okay. Right. So today's lesson is the last lesson of ionic bonding. We will then move on to, let's get rid of that. There we go. Last lesson of ionic bonding. And then we're going to be moving on to doing electrolysis. Now, electrolysis is kind of a subset of ionic because electrolysis only works with ionic compounds. But we need to box this off, do an assessment. So in today's lesson, we're going to be finally comparing melting points of ionic compounds. We're going to be looking at the charge differences. I want to actually add in there, I've deleted that. I'm also going to add ion size as well. Let's add that. Ion size. Yeah, predict higher melting point, and then we're going to do an exam question review. And as I said, I've got loads of exam questions here from past papers that we're then going to look at and be able to go through in preparation for your short assessment for your homework. I'll post the assessment straight after this lesson, and you will, it actually suddenly seems reasonable that I could actually post the assessment directly after this lesson to set you for the homework for tomorrow. That makes sense? Yeah? Get it all boxed off. It's only short. Okay, so let's crack on. So charge differences and ion size. So we've been talking about the giant ionic lattice. I'm really actually quite enjoying the pencil pen on my tablet. Okay, so we've been talking about our giant ionic lattice. Yeah. So this is the picture that you guys learned to draw. There we go. You need the symbol in there as well. So Na plus maybe, and maybe Br minus. Yeah, Na plus, Br minus, Na plus. We've been talking about this giant ionic lattice, a gill. Yeah, we do love a good gill. What we now need to realize, and hang on, once we got to that point, we then described the structure and bonding of these things. Yeah, so we described it. We actually did two questions, which was describe the structure, describe structure, and then we did explain melting point. That's what we have done so far. And what we realized is that both of these things actually rely on the same process. Yeah, for the describing structure, we run, I'm gonna change my color, Sue's structure, bonds, strength, and number. We don't bother talking about energy. You don't actually need the strength either, really, in that particular scenario. But it's nice to include it. It's nice to just have a good routine. And then when we got to melting point, we picked up structure, bonds, strength, number, and then we add on an additional one for energy. Yeah? So we're running the same process. So it's nice to remind ourselves of these things. The structure is a sodium bromide is a giant ionic lattice. Yeah, we get the point of this. Yeah, then we go bonds. It's the electrostatic attraction between oppositely charged ions. Opposite charge ions. And then we say strength. This attraction is very strong. This attraction is very strong. Yeah, and then we go number. There are millions of these attractions. That there is a perfect description of your ionic compounds. As I said, we then tack on the energy one when we're discussing melting point. Lots of energy needed to break all attractions. Notice that I switched from bonds to attractions. In the last lesson, I said bonds. They won't care in that last one. But anyway, kind of nice to do. So that's what we did last lesson. But what we now need to do is compare ionic compounds. So let's now do a comparison. So let's do comparing ionics. Okay, so let's choose somebody. Let's choose, let's go for, let's keep it simple. Let's go for sodium bromide. Sodium bromide versus sodium oxide. Notice now every single person in this room, in the exam, do we have to write S and then explain, then B, and then, oh, good question, Zaina. So Zaina, what I would actually do is, in my exam, I would actually I'd write the letters in the margin. Good question. Yeah, the margin lines running there, and I'd write the SB there, and I would just do it as bullet points. Bullet point. They need to be quality sentences. You can't just write single words. Yeah, but 5 bullet points, and then the SB, SNE in the margin, because you don't mark anything in the margin. Yeah. Okay, so it's nice to realize that we're now at the stage, guys, where you guys can build formulae. We know that sodium bromide is, sodium bromide. Let's run the process. I realize I haven't done my last 4 equations either, and this is sodium oxide. You guys are now at the stage where you're able to create these formulae. Yeah, let's just explain it. So sodium bromide as a formula is made from Na plus and Br minus. The charges cancel. It's NaBr. And then the formula for sodium oxide is Na plus and O2 minus. So that's going to be crossing down. Yeah, Na2O. I like it. So here's the question I'm going to put on the classroom. It's going to be very interesting to see if anyone can do this automatically. Would anyone like to guess on the chat which of these would have the highest melting point? Is there even going to be a difference? They're both going to be high because they're both ionic. But who's going to be higher? I wonder if anyone has an instinct. Let's draw the diagram. You can draw the picture too. I'm just drawing one repeating unit. That's all I'm going to do. They're both, I like it. Lauren, Julius, Jack, well done. Isn't that clever? They've done it automatically. So the question is, why? Well done, guys. Let's look up their values. Let's look up their values. Sodium, I have no idea what sodium bromide is. Sodium bromide melting point. Boom. 740. That beat 747. Holy guacamole. Yeah. What's going to be sodium oxide? Whoa. Well, hello there. That's going to be what? What was that? That was over 1,000. 1,132. 1,132 degrees Celsius MPT. Well done for those people. Stronger force of attraction, so more energy needed to overcome. Well done, Zaina. That's correct. So what we realize is the force of attraction, yeah, is dependent on how far apart the difference in charges is. Yeah. The difference, if we've got 0 there, and we've got 1 minus there, and +1 there, the difference in charge is 2. So the force of attraction, you could call it 2 if you like. Yeah. Look at the next one. We've now got 0. Then we've got +1, and then we've got -1, and then -2. Right. Where are my people? So I've got on this one, it was green for the positive ion and the red for the negative ion. Difference is 2. Now I've got green for the positive ion, and then I've got red for the negative ion. I've now got a difference of plus of 3. Yeah. So I now have a stronger electrostatic attraction. And look at that, almost by exactly a third too. Isn't that clever? It's an extra 50% nearly. In fact, it kind of is. That's amazing. So bigger difference in charge. So how would we write this in an exam? Yeah. The question is going to say, the question in your exam, in the GCSE exam, will say something like, sodium bromide has a higher, lower. Sodium bromide has a higher, lower melting point compared to sodium oxide. Sodium oxide. Explain, and it will be probably 4 marks. Right, so what you're going to say is, sodium, bullet point number 1, sodium bromide is made from Na plus and Br minus ions. 1 mark. Next. Na2O, nope, Na2O is made from, you could have wrote the words if you wanted, by the way, Na plus and O2 minus ions. You've got to notice that in the question, they didn't tell you what the ions were. Yet that's the first step in the answer. Can you tell them what the ions are in these compounds? Yeah, next one. The difference in charge, no, I'm just going to make it shorter. There is a bigger difference in charge between Na plus and O2 minus. Stronger. Therefore, stronger electrostatic attraction. More energy. Therefore, stronger electrostatic attraction. Therefore, more energy needed to break attractions. I'm sticking with attractions rather than bonds. Attractions in Na2O. There we go. So it is actually 4 marks, but what you realize is it's kind of 5 bullet points. Yeah. You always have to link it to energy. If they ever mention melting point, you've got to drop in energy. Yeah. Do we only draw 1 sodium and 1 oxide? Oh, yeah, good question. So in reality, if you want an entire repeating unit, you can add another one if you like. But the answer is, yeah, you only actually need to draw 1. The reason being is because in reality, we realize that these are giant ionic lattices anyway. There are millions of these in the structure anyway. Anyway, you kind of get the point. You don't need to draw any more than 1 when described, but in the lattice, when the questions you're describing all the lattices and stuff. So yeah, you only need to draw 1. Good question. Yes, they're supposed to be 2. Yeah, you can do if you like. They won't really be too fast. It's quite nice to draw a single repeating unit. Yeah, those questions do come up at times. But I hope that makes sense. Right, so we can go back to my learning objectives and tick off charge difference. Now we need to do ion size. Okay, so the next thing is it turns out if you want to have a force between 2 ions, if you have massive, well, let's do ion size. Ion size. So if you have positive and yeah, actually, let's do it like that. Don't really like that. It's too fat. Positive and negative. We know that this here is going to be the electrostatic attraction. Let's call that ES1, electrostat 1. Now let's do this one. Let's keep sodium the same. Na plus. Now let's add a bromide, Br minus. Bromine is larger. How do I know that? Because it's going down the periodic table. It's A level. As we know, as we go down the periodic table, atoms get larger. Yeah, we're adding a shell every time we drop down one. 2 shells, 3 shells, 4 shells, 5 shells. Yeah, they're getting larger as we go down the group. That's the atoms and the ions in reality. So we've always got an extra shell. So what that means is that this attraction here, I'm curious to know whether anyone could guess. So let's have a guess. I'm curious. Which one of those forces do you think is going to be stronger? Is ES1 or ES2 stronger? Based on we've now got a much bigger anion. Which one do you think is going to have the higher melting point? I'm curious to see if people can guess. Is it going to be easier or harder for sodium to hold on to that larger ion? That's the question. Is it going to be easier or harder? Is it going to be easier or harder? Julius says harder. Well done, Julius. Correct. Holding on to something bigger is much more challenging. You're having to distribute your force over a much larger area. NaCl would have the higher. Correct. Well done, Zina. Yeah. So the rule you get here is the smaller the ion, the stronger the force. The stronger the force. That's the rule. Shouldn't say the force. Stronger the electrostatic attraction. Electrostatic attraction. Because it's easier to hold on to small things than it is to hold on to large things. Is it because of reactivity? No, nothing to do with it, Jack. Nothing to do with reactivity whatsoever. It's to do with the idea of having to distribute your energies, your force. You know that this is this electrostatic attraction. Yeah. So if you imagine this like a force, you could say, you know, with chloride, yeah, the force is being distributed over, you know, this area. Whereas now his force is having to be distributed over a much larger area. So it's not going to be able to be held quite so tightly. Imagine holding onto a tennis ball. Imagine I took Jack and I gave Jack a tennis ball. It's got a short leg. Yeah, I gave Jack a tennis ball to hold on to. Gave Jack a tennis ball to hold on to. And I said, I want you to hold on to that with dear life. Yeah, what Jack will do is he will clamp his hands really tightly around that object. Yeah, and he will apply all his force onto a small one. Yeah, but if I then gave Jack a beach ball to hold on to, yeah, if I gave Jack a beach ball to hold on to, all of a sudden there becomes a real problem because he's having to hold on to an object much, much larger. So holding on to small things is much easier than holding on to, because he's having to distribute his force around the whole object. So instead of applying it kind of entirely over there like that, yeah, he's only able to apply it on a much smaller object like this. Does that make sense? Wow, I look so slim. Must have been working out. Yeah, it's so true, Jack. So true. Yeah, so true. In reality, of course, holding onto the beach ball, I think you're less happy about. Yeah. So the rule is smaller the ion, the stronger the electrostatic attraction. So we can now predict other compounds as well as a result of this. And this is all you need to be able to do. Let's do Let's do sodium chloride versus potassium chloride. Right. So what we need to do is look at who it's made from. So we've got sodium ions. How many shells does sodium have? Sodium has 1, 2, 3 shells. Oh, but it loses one. Sodium only has 2 shells. Sodium only has 2 shells because it's lost its third. It's shrunk in size. Yeah? And then we've got chlorine with 3 shells, and that one's now ballooned in size. It's massive. Yeah, there's chloride with its extra electron in the outer shell from sodium. There we go. Dot and cross Lewis. Let's look at now potassium. Where's potassium? Potassium's bigger. Started with 4, now only got 3. But it's larger. So there's the potassium ion. And then the chloride ion is exactly the same. So at this point, we can make a prediction. Yeah, we can just go 1, 2. 1, 2, 3. Didn't do that very well to keep it the same size. It's fine. Yeah, there's the chloride. So the first thing we can do is discount the chloride. It's the same. Don't worry about it. But now we can say, now there's a size difference. Yeah, so sodium chloride should be higher than potassium chloride. Let's check. Let's do sodium chloride is 801. 801, there we go. But potassium chloride should be lower. 770, there you go. So we've got 801 for that guy and 770 for that. It is slightly lower because it has a larger cation. I hope that makes sense. That actually brings us to the end of ionics. Brings us to the end of ionics, which is nice. So now what I want to do is, now that we've kind of discussed that, and I said the only bullet point fact I want is that the rule is the smaller the ion, the stronger the attraction. Yeah? So let's have now that we're done, let's have a look at the, there we go. So we've done ion size. We have, changed the size of my pen. We have done the ion size. We have predicted melting points. We can predict. All we now need to do is do an exam review. So okay. Right, so I've just got a whole load of exam questions here, guys, that I'm just going to run through. Just taking them from various papers. Okay, question number 1. So it's nice for me to flag up the questions you're going to have on your test. You will definitely have one of these. Convert from word to symbol. Yeah, it's going to happen. So each one, this is where I shouldn't really have stacked them quite so close together. Oh, no. Oh, no. I'm going to drag it over to there. There we go. From word to symbol. Guys, what I'd like you to do is this exam review. I want you to take this as an opportunity to be able to, A, check test to see whether or not you're doing the right thing, but also to build and repair data. So if I bring up a question and you think you can do it, pause the video, have a go, and then watch back the answer to see if you get it correct. If you have no idea what I'm doing, then you can watch the video and then I can give you a second one for you to have a go at. So I need to convert this word equation to a symbol equation. Right. So what ions are in it? K plus, OH minus, charges cancel, plus, HCl, hydrochloric acid. Hydrogen is H plus. Yeah, hydrogen's always H plus. So we've got H plus and Cl minus, charges cancel. Right, potassium chloride, K plus and Cl minus, charges cancel, KCl. And water, H plus and O2 minus, H2O, like it. Right, now we need to, don't forget to balance if needed. 1 potassium, 1 potassium, 1 oxygen, 1 oxygen, 2 hydrogens, 1 chlorine. It already balances. How nice is that? Oh, that's very typical. It's already balanced. I know, right? So isn't that great? So by the way, all of this in your answer all of that disappears in your exam. Do not leave any of that. That is your final answer, the balanced symbol equation with no charges in it. Yeah? Very common things that I keep seeing students do is leaving charges all over the place. If you do that, you'll lose it. Please don't. In chemical equations, there are no charge ions. Yeah, it's all cancelled out by the formulae. Okay, next one. Ammonium nitrate is another salt. Ammonium nitrate is made with ammonia, is neutralized with an acid. Name the acid. I wonder how many people on the chat are going to know this one. I taught you lesson 101 with me at the very start of the year. I said, learn your acids. Yeah, to make a nitrate, you're going to need nitric acid. Know your acids, folks. You've got to know it. Nitric acid. Oh, I've written acid. Lol, that's hilarious. There we go, nitric. Next, draw the complete diagram to show the electronic structure of a chloride ion. Okay, so chloride, seal in the middle, 2 electrons in the inner first shell, 8 electrons in the second shell. And then there would normally be, for a chlorine atom, there would be 7. That's a chlorine atom. But for a chloride ion, it gains a circle. Put it in a square bracket and add the 1 minus. Lots of students forget the square bracket and the charge, and it needs to be there. All that there for 1 mark. Next, describe the structure and bonding in sodium chloride. Perfect. Okay, NaCl. So, describe the structure and bonding. Perfect. Bullet points. Susan, Boyle, Sings, Nelly. I don't need to do energy because there was no mention of melting point. So, the structure. Now remember, these must be full sentences. And this is where Zina's question comes into play. There's the border of your exam. I write these letters. I'm actually going to write the letters one by one, because if I do that, it means if I go onto another line, that's okay. So structure. Sodium chloride. I'm actually going to write the words. Yeah, sodium. I'm trying to pen a bit thicker. Sodium chloride is a giant ionic lattice structure. I'm actually lobbing in the word structure at the end. Love it. Next, bonds. I'm going to bullet point it. Held together by the electrostatic attraction. That's why I wanted to not do the letters all in one go. Electrostatic attraction between Na plus ions and Cl minus ions. They've put me in a context, folks. So if you'd put oppositely charged ions, they probably wouldn't mind opposite charge ions. They probably wouldn't mind that. But since they've given me a context, I may as well say who the ions are, because we know them anyway. Next, strength. This attraction is very strong. Bonds. There are structure, bond, strength, and number. It's very strong. There are millions. There are millions of these attractions. Perfect. We're done. 4 marks. Don't need energy. Next. Very normal. So they're just wanting a word equation now here, guys. By the way, if that word wasn't there, if the word if they just said complete the equation, they would mean symbol, unless of course they've got a word in there anyway. But essentially, if they say the word equation at GCSE, you're not in years 7 and 8 anymore. You're not in key stage 3. Chemistry now, unless they say the word, you're writing it as a symbol. Yeah. Okay, so it says sodium reacts with fluorine to produce sodium fluoride. Complete the word equation. They literally have done exactly what I did with you before. Yeah, fluorine. It's ridiculous, isn't it? They're testing you to see if you know which one are reactants and products. That's all they're doing. We're done. Next, sodium fluoride. Oh, I love this one. I hope you guys had a chance to look around the house for ionics, because I actually missed a property, and it's the reason why I missed it. I actually missed it deliberately, but then the question came up on one of the papers. Sodium fluoride is an ionic solid, an ionic substance. What are two properties of ionic substances? So I'm going to put this one on the chat. I know that there's going to be loads of delays now, but I wonder who's going to be able to spot this, because it asks for two. And I'm hoping you can pick one of them straight away, but then I wonder if you can figure out what the other is. Yeah, because there's one there that I haven't taught you, but you should be able to figure it out by the process of elimination. Who's going to pick them out for me first? I know that there's a big delay. High melting point and dissolves in water. Well done, Zina. It's a clever trick, isn't it? I never mentioned that ionic substances tend to dissolve in water. High melting point dissolves in water. Well done, Owen. Great job. So I never mentioned this. Now, not all ionic substances dissolve in water, but most do. Yeah, the rule is that everything is soluble unless you've got an exception. Don't ask. We do solubility rules way later on, year 11. But most of them dissolve in water. Just to actually let you know that the rule for fluorides, all fluorides are soluble. So they always dissolve in water, no matter who they're bound to. Calcium fluoride, magnesium fluoride, potassium fluoride, ammonium fluoride, they're always soluble. So yeah, clever question now. Next, complete the word equation. So once again, they're just looking you to be able to analyze what's going on over here. Yeah, lead iodide is produced by mixing two solutions, complete the words. They're just looking to see if you can flip them around. So we're going to have started off with lead nitrate, it's a displacement, and having potassium iodide. Yeah, you just reverse them. Yeah, there's no acids in here. It would be different if it was an acid involved, but simply because there isn't, it's just swap the females, swap the non-metals. Next, a student found that potassium chloride does not conduct electricity. Explain why, use the words. The solid potassium chloride does not conduct electricity because the ions, this is pretty easy, cannot move. Yeah, are too big. Lol. Oh, lol. Have no charge. Ugh, what? Stupido. Yeah, that answer there is stupido. That's, yeah, cannot move. What could the student do to potassium chloride to make it conduct electricity? Now that one I find more entertaining. Wonder who could give me that one on the chat. What could the student do to potassium chloride to make it conduct electricity? 1 mark. Can I just point out, by the way, there were 2 correct answers. There isn't really, actually. Do you know what? I tell a lie. I tell a lie. There is only really 1 correct answer. I'd love to see the mark scheme for that one and see if they accept it. Put it in water or melt. Well done, Owen. Owen, which one do you think? Dissolve it in water. See, Masaru's picked that one over melting it. The problem is if you're mixing with water, you're adding it to something else. If it's just saying, what could a student do to make it conduct? I think they'd allow it. Can I just point out the top answer here is melt it. That's the top answer. but I'm pretty sure they'll allow both. You need to know both. Yeah, make it dissolve in water. So melt or dissolve in water. Fine. During electrolysis, why do potassium ions move to the negative electrode? On the chat. Opposite charges attract. Thank you very much, Masaru. That's correct. Opposite charges attract. Opposite charges attract. Thank you very much. So we've got the positive cation of potassium being attracted towards the negative electrode. Yeah, this is the negative electrode. So there's going to be an attraction. Opposite charges attract. That's it. Electrostatic attraction. Yes, absolutely. Gayatri, you'd want to say electrostatic attraction, brackets, opposite charges attract. Yeah, it's the opposite charges which I really, really want you to focus on there. But it'll be interesting if they accepted that on the marks scheme. I'll check the marks scheme for that one as well. But the answer I'm looking to support there is opposite charges attract. Yeah. Right. Okay, big question. Okay. Soda glass is described as a giant ionic lattice with a melting point of 660 degrees Celsius. Explain the high melting point. Okay. Susan, Boyle, we're out of space. Susan, structure. So, they've already given it to me. Oh, that's clever, isn't it? Hence why it's only 4. Huh. I'd still write it down. I'd still do it. I'd just repeat it. I like my routine. Soda glass is a giant ionic lattice structure held together by the electrode. Now, this is interesting. They haven't told us what the ions are now. See what they've done. Held together by the electrostatic attraction between oppositely charged ions. Between opposite charge ions. We don't need to mention with the last one, we put it in a context. But this one, they haven't even told us what the ions are. So we just assume they're oppositely charged because it's ionic. So we just do it that way. Strength. The electrostatic attraction is very strong. The electrostatic attraction is very strong. Electrostatic attraction is very strong. There are millions. There are millions of these attractions. Lots of energy needed to break all attractions. We're done. 4 marks. 1, 2, 3, 4. Boom. Thank you very much. We don't get one for the first one because they had already told it to us. Oh, rather clever. I like that. It's a really nice question. Really lovely. Suggest a method. Oh, it's a continuation. Suggest a method to prove soda glass contains ions. Love it. We've already had this today in this lesson. On the chat, please. I wonder who can tell me. Suggest a method to prove that soda glass contains ions. 2 marks, 2 bullet points. Sir, for the 4 mark, do we have to include the last one? God, yes. Yes. Energy. As soon as they see it, as soon as you see melting point, you've got to mention energy, Jack. Got to. If they don't, they ask you to describe the structure. This one was simply describe the structure. Yeah, no mention of melting point, no need for energy. But it's 4 marks. Yes. Bonds. In this case, it should be 5. Giant ionic lattice, 1. Yeah. Bonds, strength, number, energy, 4 marks. We don't need the first one, Jack, because they told us it in the question. See if it dissolves in water. No, Zina, that is not correct. Because sugar dissolves in water, and that's not ionic. Maybe electrolysis. Right, 2 marks, guys. If it shatters, no, sugar shatters. Can't do it. If I take a big piece of sugar and throw it on the floor, it'll shatter. Can't do it. That's not ionic. There's only one proof that something is ionic. Just one. Only one real proof. Melt it. Melt the soda glass. Melt. Why did I do that? Melt the soda glass and see if it conducts electricity. The only real test to see if something's ionic. Yeah? Because the problem is, all the other properties are great. And don't get me wrong. Look at that. Give 2 other properties of ionic compounds. Right, hang on a minute. 2 other properties. So they've already given us the high melting point, because it was the clever thing is the other. Yeah, and you can't use that. You're not meant to use conductivity either, because you've used it in that. Oh, it's really hard. Level 8, 9 there, guys. Level 8, 9. So first one, everyone will get at least 1. Brittle. Yeah, that's important. Brittle. Oh, and I never told you. They're very strong. Isn't that interesting? Have you guys ever been on those glass walkway? Have you guys ever been on a glass walkway? Yeah, they're the most ridiculously terrifying things ever. Like, seriously, who thought that was a good idea? Like, I don't get it. Like, yeah, that's a great idea. Let's make the whole walkway out of glass. Yeah. Have you guys also been, oh my goodness, that's so mean. Yeah, but glass walkways, you can do it. Looks like you'll fall, exactly. So you can do it because they are very, very, very strong. Have you seen how thick the glass is? It's terrifying. Yeah, it's so thick. But if it did break, like, have you ever seen, so I'll tell you a quick story. Oh, we're running out of time. I went up the CN Tower in Toronto, and the CN Tower has a glass floor. And I went up the CN Tower, it's a big tall building. Yeah, there's the glass floor in the CN Tower. And I went there, and of course, when I walked in, I was standing on this glass floor, and there were just kids jumping up and down on the glass. Why would they do that? What in total insanity? It's like, yeah, let's see if we can break it. And I don't know about you guys, but I'm literally watching these kids jump up and down on this floor going, please break, please break. Just, kids. I'm pretty sure that everyone in the entire room was all watching these kids hop up and down on the glass floor. We were all, as one, thinking, die. Ugh. Like, it's just like, ugh. Anyway. Sodium reacts. Last question, I think. Yeah, last question for the lesson and we're done. Sodium reacts with both oxygen and chlorine to produce ionic compounds. Explain using your understanding of ionic bonding which compound, sodium oxide or sodium chloride, would have the higher melting point. Right. 5 marks. Holy guacamole. First mark. They haven't told us who's in what. Sodium oxide contains Na plus and O2 minus. Sodium chloride contains Na plus and Cl minus. 1 mark for that, 1 mark for that. Amazing. 2 marks down already. Next. Bigger difference in charge. Yeah. Bigger difference. I'll be good. I've only got 3 minutes. Bigger difference in charge between Na plus and O2 minus. Stronger electrostatic, attract. You can't do that in your exam. Yeah, stronger electrostatic. And Explain your understanding about which. We haven't actually said it. Therefore, Na2O has a higher MPT, melting point. You can't do MPT in your exam either. Melting point. 5 marks. Tick, tick, and tick. We're done. Right, guys, that's the end of the lesson today. So I've done all my learning objectives, which I'm really pleased with. I hope you guys have found it useful. I hope you have found it all useful, guys. I will post your test on the classroom now, guys. Good luck. It's only you can take as much time as you need to do it. Just I prefer you not. In fact, do not look at your notes. Yeah, that's the point. I don't mind how long it takes you, as long as you don't cheat. That's it, guys. Have a good rest of your day. When is it due? Tomorrow. No. I'd like it to be done. I'd like to go through it tomorrow, Gayatri. It's not very long. It's literally 2 pages. Won't take you very long. Please, please, please. Anyway, guys, I'll see you soon. If you can't do it tonight, don't worry about it. But I'll see you guys. Have a nice rest of your day. Have a nice rest of your day. I'll see you soon.